Okay, so what we're going to take a look at is investigating the relationship between the length of a conductor and its resistance. So just to show you what we've got set up here, so what we've got set up is we've got a 1.5 volt EMF cell in here, and the reason we've got a small EMF is we want a small current in our circuit so that our wire doesn't get too hot and the temperature then changes its resistance. Because what we want to make sure is in this experiment we want the length to be able to affect the resistance, and we want to make sure nothing else affects resistance. So we're going to try and keep the temperature low, stop that affecting its resistance. And we've got an ammeter here and a voltmeter in here to enable us to calculate what the resistance is at any length of wire that we choose. So you can see I've got myself set up a table here. I've got this column on the right hand side, and you will see why I've added that later on, but we'll get started collecting some data. Okay, so if we take a look at the equipment that we've got, so you can see we've got our 1.5 volt cell over here. This is our voltmeter, which is in parallel with this wire that you probably can't see running along this ruler. And then what we've got over here is an ammeter that I haven't yet plugged in because I don't want a current in our circuit heating up the wire while I'm not doing anything. So let's get that plugged in. So at the moment, this wire, to measure its length, you need to make sure you pull it tight because it's very pinked. So this is currently at a length of 0.5 meters or 50.0 centimeters, because I can measure to the nearest millimeter. So I should be writing in my table 50.0 because I said I was measuring in centimeters. You will see in a minute I wrote down 0.5 because I'm a spanner, first of all. Okay, so let's get our circuit actually plugged in. I am going to plug it in the 5 amp setting because I don't know how big the current is, but I'm expecting it to be quite big because this wire resistance will be very small. So looking at this here, so if I bring this a little bit closer, we're plugged into the 5, so I'm reading on the bottom scale. So you can see it's about half an amp, which means I'm allowed to put this now on the more sensitive setting because it's less than 1 amp, so that's nice. So for 50 centimeters, you can see we've got a current, so that's 3.8 on the scale, so that's 0.38 amps. And then our voltmeter is 0.94. So I'm just going to do the calculation straight away. So I'm going to do 0.94 divided by, the current has actually changed slightly. The current is now 0.4, so 0.40, giving us a resistance of 2.4 ohms at this particular length. So what I'm going to do now is I am going to halve the length. And the reason I'm going to do that is I want to explore whether there's a direct proportionality or an inverse proportionality between length and resistance. So halving the length is a really useful way to do that. I will also be doubling it in a second, so I'll do a full meter as well. So again, making sure we pull the wire tight. There we go. So I've got 25 centimeters in there, so let's put 25.0 in our table. So on this, I've got a potential difference of 0.79, and I've got a current, so it's 7.4 on the scale, so that means it's 0.74 amps. So let's do 0.82, which is what the potential difference is reading now, divided by, what's this actually reading? It's settled now on actually 0.7, so let's put 0.7 in. And we've got its resistance is now 1.2 ohms. So if we actually look at our data now, you can see that when we halved the resistance, halved the length, it looks like we've halved the resistance. So that's looking like a directly proportional relationship. So let's try it the other way. So let's actually get our length all the way up to a meter. So while I'm doing this, have a think for yourself. What value are you expecting for the resistance at this length? Make a prediction. That's pretty much a meter. Okay, so in terms of the readings that I'm seeing here, so we're at 100.0. So I've got a potential difference of 1.03 and I've got a current of 0.2, giving us a resistance of 5.2 ohms there. So you can see whether or not that matches up with your prediction. Now I'm just going to throw in a couple more lengths. It's always good to have a little bit more data. So let's do 75. You can do any lengths you want in this experiment. It really doesn't matter, but it's good to have a range. So I've got a potential difference of 1.02. I've got a current of 0.26, giving me, so 75.0 centimeters. So our resistance is 3.9. Let's do one more. And let's have a really small one. So I'm going to do 5 centimeters here. So let's have a really small length. Okay, so 5 centimeters. Okay, so 5 centimeters gives me a potential difference of, what's that, 0.35. And it gives me a current of, okay, my potential difference is kicked up, so it's now 0.39, and I've got a current of 0.99. So that gives me a resistance of 0.40 once I've rounded it to significant figures there. I'm just going to quickly check that this hasn't gone off the top of the scale, which it might have done. So I'm just going to quickly check that. No, it hasn't. That is the 0.9 is absolutely correct. So that's fine. So what we've got now is we've got a series of potential differences and not potential differences. We've got a series of lengths and a series of resistances. So I said before that I thought this was directly proportional because when I halved the length, I halved the resistance. So the way we check for a directly proportional relationship is I'm going to calculate R over L, which would be measured in ohms per, in this case, centimetre, because I've got my lengths in centimetres. Okay, I could have done L over R, it makes no difference. I've just picked R over L arbitrarily. As long as you will do one divided by the other, it really doesn't matter. So what I'm going to do is we're going to calculate values here, and we're going to see what we'll do with that. So I'm going to pause it while I calculate them, because otherwise we're just wasting time. Okay, so if we look at our results, we can see that for these four here, the value of R over L is constant, okay? Certainly within experimental uncertainty. So I wouldn't expect to get the exact same thing, but you can see our values have been pretty close every time. And so what I've been doing here is the test for direct proportionality. So if you think two things are directly proportional, if you calculate the ratio of them, it should come out the same value for any piece of data that you've collected. Now the anomaly you can see here looks like this one here. So you can see that that value has changed. So my suggestion would be here is that we've got temperature effect. And the reason I think that is because this is for the shortest length. So this one has the lowest resistance, and so there's the highest current in this circuit. And that's going to mean the wire is going to be at its hottest, which could affect its resistance. So that would be my prediction for why we've got that value there. But looks like we've got pretty good data showing a directly proportional relationship. So why is it useful to find a directly proportional relationship? Well, what this means is we can now write an equation between resistance and length. So we can write an equation in this form here. So we don't know what this is. So this is just some constant. So this is, so basically we can calculate resistance if we know the length. So in this experiment, we've actually found out what that constant is. So that this constant is approximately 0.05 ohms per centimetre. So what that means is I could plug any length into this equation and it should tell us what the resistance is. So for instance, if I put in a length of 25, so let's try that. So let's do 25 times 0.05 You can see it predicts that the resistance should be about 1.25. Well, if we go to our table, you see we got a value of 1.2 when we actually measured it. So you can see this equation now allows us to predict the resistance of any length of wire, as long as we've got the length measured in centimetres there. But what our data suggests is that this probably doesn't work that well for short lengths because temperature is starting to affect our results. So that would be our outcome of our experiment, and we've found ourselves a relationship between resistors and length.